Assalamualaikum, good day to all. So for this lecture, we're going to cover our second part of chapter 5 with regards to the lossy compression algorithm. Okay, so the outlines for this lecture is going to cover on the lossy compression algorithms, and first part we're going to cover on the compression with the DFT. If you guys still can remember, we already covered the DFT in previous two lectures. And after that, I'm going to share with you with regards to the discrete cosine transform or DCT and also JPEG compression. So lossless compression algorithms does not deliver compression ratios that are high enough. Hence, most multimedia compression algorithms are lossy. So what is actually lossy compression? So the lossy compression is actually the compressed data is not the same as the original data, but a close approximations of the original data perceptually. So this lossy compression is actually yields a much higher compression ratio compared to the lossless compression. So here I just reflect back on the data compression methods that we already go through previously under the lossless compression methods, and also today we're going to cover on the lossy and specifically in the JPEG compression. Okay, so how actually to measure the quality of this lossy compression? We use distortion measures. So what is actually distortion measures ni? A distortion measure is a mathematical quantity that specifies how close an approximation to its original data. So there are three most commonly used of distortion measures, which are mean square error or MSE, signal to noise ratio NSR, and peak signal to noise ratio PSNR. So for SME, the lower the value of SME that we get, the lower the error between the compressed signal and uncompressed signal. While for the SNR, the higher the value of the SNR that we get means that the algorithm, this SNR algorithm offer a better performance. While for the PSNR, the higher the value of PSNR that we get, the better the quality of compressed or reconstructed signals. So apa maksud ni? Kita akan go through exercise lepas ni on how actually to read it. Okay. Okay. So move on to the transform coding. So what is actually transform coding? Transform coding is a two-dimensional or 2D compression technique that first switches the image to the frequency domain, then compress the image. So transformation of frequency domain can be done via two ways. First, by using the DFT or discrete Fourier transform, and second, by using discrete cosine transform. Okay. So first one, how actually to do or to conduct the compression using DFT. So image compression can be carried out using two-dimensional fast Fourier transform or FFT by considering only a few of the Fourier coefficients. So for example here, so let's say we have a 2D signals fxy. So this is the value for 9 data, okay, for 2D signals. Okay. So first step to conduct the compression with DFT, we compute the Fourier coefficient for the 2D signal to find the FUV. So if you guys still remember, let me open the Fourier transform exercise. Okay, so here using the Fourier transform, we calculate the magnitude. Okay, so where we have here the value of the real and imaginary value. Okay. Okay, so here when we compute the Fourier coefficient, we get the real and imaginary value. Okay, so next step, second step, we compute the magnitude. We calculate the magnitude for each of the value using Fourier coefficient. So the magnitude for FUV, this is the value. So step 3, we calculate the mean of the magnitudes. So to calculate the mean equals to sums of the all magnitudes that we get divide by the size of the magnitude. So here the size is 9. So we get the mean 1.39. To step number 3, we calculate the mean. Okay, so based on the mean that we get in step 4, we find the magnitude they are more than the mean value. So here assign the other magnitudes to 0, which means semua value magnitude yang besar daripada mean value kita remainkan. Value yang rendah daripada mean value dia tadi kita dapat 1.39, we replace it with 0 magnitude. Okay, so based on this value in step 5, again we calculate the Fourier coefficient of the magnitudes in step 4. So when we calculate the Fourier coefficient, of course we're going to get the value based on the real plus imaginary value. So next step, step 6, we calculate the inverse Fourier transform using Fourier coefficient in step 5. So the results of two-dimensional or 2D signal compression using Fourier transform is this one. Okay, so this is the result. So based on this is the value before the compression and this is the value after the compression. So based on this, we're going to calculate the MSE dan juga PSNR. So how actually to calculate the MSE? We deduct before compression and after compression for each of the magnitude. Okay, so here kita ada 9 magnitude, hasil deduct first magnitude plus second magnitude, hasil deducted until 9 magnitude dan power of 2 we divide by 9. So we get the value of 0.5042. So based on this MSE value, we can further calculate the peak signals to ratio, noise ratio or PSNR. So how to calculate the PSNR? 10 log 10 255 power of 3 divided by the MSE value. So here we get the value of 54.89. So here based on the slide earlier, it states that the higher the PSNR value, the better the quality of compressed or reconstructed signals. So for example, if we have asked you to compare between two signals compression, first one kita dapat ini 54.89. Second result for example kita dapat 80. So which one is better compression? Of course the second one, for example. Okay, so the higher the value of PSNR, the better compress of the signal. Okay, semua faham there is actually, in order to conduct or to perform the FT, kita ada 6 steps. Lepas tu we calculate the MSE and PSNR. Okay, so next tadi first method to calculate the lossy compression. Second method or second technique is to use discrete cosine transform or DCT. So DCT, discrete cosine transform, is similar to DFT since it decomposes a signal into a series of harmonic cosine functions. But DCT is actually a cut down version of Fourier transform. For DCT, it's only focus or only use the real part of the Fourier transform. Which means when we calculate the Fourier transform, jadi senang, kita ada real plus imaginary kan. So for DCT, they just only use the real part sahaja. Okay, so DCT is computationally simpler compared to the Fourier transform. DCT is effective for multimedia compression because much more energy compaction, and DCT is much more commonly used compared to the Fourier transform, especially in multimedia image or video compression. Okay, so this is actually the formula to calculate one-dimensional DCT. Okay, so here this is the first one to calculate the 1DCT formula, and below is the inverse 1D DCT. Okay. Okay, so here, for example, on calculating the 1D DCT. So let's consider a signal in a time domain that has a constant amplitude of 100. So we can say that Fi equals to 100 for I equals to 0 until 7. Okay, so the domain of 0, 7 for I. So we therefore have n samples. We have n. Why samples n? We have 8. Why 8? Because from 0 until 7. And we will need to work 8 values for u equals to 0 until 7. Okay, so based on this value, first we calculate the F0. Okay, so we calculate the F0 using the 1D DCT formula and we get 283. So next, we further calculate the F1 until F7 using the 1D DCT formula. So the result is 0. Okay, so here after that, we plot the FU. So here we can see based on the plotting, because all the values from F1 until 7 is 0 and only F0 holds the value of 280. So dia akan dapat horizontal line macam ni saja when we plot it. Okay. So this is 1D DCT. Okay, so now move on to the two-dimensional DCT. So quite similar to the discrete Fourier transform for 2D DCT, okay, so where in two-dimensional DCT, it transforms a signal or image from the spatial domain to the frequency domain. Okay, so the input image is n by m, where Fij is the intensity of the pixel in row I and column J in spatial domain. And the FUV is the DCT coefficient in row U and column V for the DCT matrix. Okay, so for JPEG image and MPEG video, the DCT input is usually an 8 times 8 or 16 times 16 array of integers. Usually kita akan gunakan 8 times 8. Okay, kita akan pecahkan kita punya pixel tu kepada 8 times 8. Okay, usually yang most or yang you guys akan guna adalah 8 times 8. Okay, so in 2D DCT, this is the formula to calculate two-dimensional DCT, and this below part is the inverse 2D DCT. Okay, so one of the properties of 2D DCT is it is separable. Maksudnya, which means it can be separated into a pair of 1D DCT. So to obtain the 2D or two-dimensional DCT of a block of 1D DCT is first performed on the rows of the block, and after that 1D DCT is performed on the column of the resulting block. So this step is the same, applies to the inverse DCT. So first based on this, dia akan baca dulu based on the row and after that based on the column. Okay. So move on to the types of DCT, which is JPEG compression. So what is JPEG? JPEG ini actually stand for what? JPEG stand for Joint Photographic Expert Group, which is an international standard since 1992. So this JPEG implies DCT, Discrete Cosine Transform, to compress the images. So make use of the fact that human eyes is less sensitive to a higher frequency information. So therefore, for JPEG, is actually use this high frequency and compress it. Okay. So to work with colors and grayscale images, JPEG works with, of course, it will work with colors and images, grayscale images, and also JPEG suitable for compression of satellite images, medical images, and general photos. Okay, So this is actually the basic JPEG compression pipeline ataupun dia punya steps. Okay, so based on this, I'm going to let you guys to refer or to view the explanation from our resource persons for this subject. Okay. Okay, so here the summarize of the JPEG image compression steps. First, we transform the RGB to YIQ or YUV, and after that we subtract 128 from each pixel in image block, and after that we apply DCT. Apply DCT, which means we apply the 2D DCT on image block. Okay, the results of it, we further apply the quantization. So the results of based on the result we get from the quantization, we do the zigzag ordering and run length encoding, and after that we implement entropy coding. So no worries, we're going to go through step by steps after this. So first step 1, transform the RGB to YIQ or YUV. So here, for example, we have a picture. So we extract the 8x8 pixel blocks of Y component from the image. So for example here, 1 blocks, we extract it into 8x8 pixel. So this is, for example, the data of 8x8 data block. Okay. So step 2, for each block, subtract 128 from each of pixels in image block. So here, which means 52 minus 128, we got negative 76. So kita akan buat for each of 8x8 blocks ni, kita akan tolak 128. So this is the results. Okay. Okay, so now step 3. Apply 2D DCT to get DCT coefficient matrix. So here, the 2D DCT is applied to each block image, Fij, with output being the DCT coefficient FUV for each block. So which means we apply the 2D to get the coefficient matrix. So this is the results of 8x8 DCT coefficient matrix. Okay, so step 4, we're going to perform quantization. So quantization is actually helps to reduce the amounts of information in higher frequency DCT coefficient components using a default quantization matrix. So to calculate the quantization is actually the image matrix FUV divided by quantization matrix QUV, where we're going to round it. Contohnya kalau the results of this division, you guys divide dapat 5.6, so we round it jadi 6. Kalau 5.3, kita roundkan dia jadi 5. So we round. Just we going to read the quantization based on the nombor bulat. Going to round it. So for quantization matrix, we have two parts of the quantization. We have luminance quantization matrix and also chrominance quantization matrix. So this is actually the default value that yang akan digunakan to calculate the quantization. Okay, so here this is the 8x8 DCT coefficient matrix that we get earlier. Okay, so we divide the image, we divide with the quantization, default quantization luminance matrix. So we get the quantized 8x8 DCT coefficient matrix. Okay, so after quantization, we can see that much of the signal energy lies at lower frequencies. This appears that the upper left corner of the DCT. So which means after we do the quantization, we can see that dekat atas ni, upper left corner of the DCT holds the low frequency, while the lower holds the high frequency. So the compression is achieved since the lower right values that represent higher frequency and are often small, which is small enough to be neglected. So this is actually the place or the part that we're going to compress it. Okay, so after that we implement zigzag ordering. Okay, so the components of quantized DCT coefficient matrix is read or arrange in zigzag order. So if you guys can see, inilah zigzag order ni, daripada first column, next, turun ke bawah, okay, do zigzagging until last block, okay. So here, based on the quantized data, quantized DCT coefficient matrix, we arrange it in zigzag ordering. Start from 0 until 15. Okay. Okay, so here, saya conteng sikit macam mana nak buat dia. Daripada 26 ke 3, turun 0, turun 3, naik 2, 6, next, turun 4, 1, 4, turun 1, so on and so forth. You guys kena buat dia betul supaya nanti nak susun value dia baru boleh jadi betul. So saya buat, Allah Akbar, sanggup tak? Tidak. Okay. So until the end lah, dah lari pula arrow saya. So bila baca kat atas ni, negatif 26 minus 3. Lepas tu next value adalah kosong sini. Lepas tu negatif 3. Lepas tu naik atas negatif 2, naik atas negatif 6, next 2. Okay, dia akan baca susun value based on this zigzag. So kena buat zigzag ini dengan betul. Nanti kita do exercise on zigzag ordering ni. Okay. Okay. So based on this last step adalah kita akan run length encoding or RLE. So based on the zigzag ordering result, okay, we implement the RLE. So how to do the RLE? So here you guys can see RLE dia akan listkan balik dan dia akan compresskan. Maksudnya adalah negative 26, negative 26, minus 3, minus 3, 0, minus 3. Okay, kat sini semua sama lagi, tak ada redundant lagi. Okay, when it comes after minus 4, 1 dah ada 2. So dia akan tulis sini 2 ones. 5, and then dekat 5 ada 0. Banyak dipik 0 sini. 1, 2, 3, 4, 5. 5 kali 0. So dia akan tulis 5 zeros. And after that, 2 minus 1 and 38 zeros. Okay. So this is the result of the run length encoding DCT coefficient. And we have to repeat this procedure, okay, for all of the 8 times 8 block. Yang sekarang ni kita baru buat untuk satu piece, satu block tu sahaja. Satu block of the picture just now. Okay. So that's all. So let's recap back a bit. So on today's lecture, we covered on the compression with the DFT. And then we go through one-dimensional DCT, two-dimensional DCT, dan juga JPEG compression. Di mana JPEG compression ni menggunakan 2D DCT. Okay. Thank you.